And let's say that I do it counterclockwise so that it will, it will match with the statement of the theorem. And let's say that I want you to compute the line integral along C of y e to the minus x dx plus 1/2 of x squared minus e to the minus x dy. And, that's a kind of a sadistic example, but maybe I will ask you to do that. So how would you do it directly? Well, to do it directly, you would have to parameterize this curve. So that would probably involve, setting x equals 2 plus cosine theta, y equals sine theta. But, I'm using as parameter the angle around the circle. It's like the unit circle, the usual one, but shifted by 2 in the x direction. And then I would set dx equals minus sine theta d theta. I would set dy equals cos theta d theta. And I would substitute, and I would integrate from 0 to 2 pi. And I would probably run into a bit of trouble because I would have these e to the minus x, which would give me something that I really don't want to integrate. So instead of doing that, which looks pretty much doomed, I'm going to use Green's theorem. So using Green's theorem, the way I will do it is I will instead compute a double integral. Okay. So I will compute the double integral over the region inside of curl f dA. So I should say probably what f was. So let's call this m, let's call this n, and then I will actually just use the form in coordinates, nx minus my dA. And what is R here? Well, R is the disk in here. Okay, so of course, it might not be that pleasant because we'll also have to set up this double integral. And for that, we'll have to figure out a way to slice this region nicely. We could do it dx dy, we could do it dy dx, or maybe we will want to actually make a change of variables to first shift this to the origin, change x to x minus 2, and then switch to polar coordinates. Well, let's see what happens later. Okay? So this is R. So what is n sub x? Well, n sub x is x plus e to the minus x minus, what is m sub y? E to the minus x, okay? This is nx. This is my dA. Well, it seems to simplify a bit, right? I will just get double integral over R of x dA, which looks suddenly a lot more pleasant. And of course, I made up the example in that way, so that it simplifies when you use Green's theorem. But that gives you an example where you can turn a really hard line integral into an easier double integral. Now, how do we compute that double integral? Oops. Well, so one way would be to set it up, or let's actually be a bit smarter and observe that this is actually the area of the region R times the x-coordinate of its center of mass. Right? If I look at the definition of the center of mass, it's the average value of x, so it's 1 over the area times the double integral of x dA. Well, possibly with a density, but here I'm taking uniform density 1. And now I think I know, just by looking at the picture, where the center of mass of this circle will be, right? I mean, it will be right in the middle. So that is 2, if you want, by symmetry. And the area of this guy is just pi because it's a disk of radius 1. So I will just get 2 pi. I mean, of course, if you didn't see that, then you could also compute that double integral directly. It's a nice exercise. But see, here using geometry helps you to actually streamline the calculation. Okay, any questions? Yes?
The last part.
Okay, yes, let me just repeat the last part. So I said we have to compute the double integral of x dA over this region here, which is a disk of radius 1 centered at this point is 2, 0. So instead of setting up the integral, with bounds and integrating dx dy or dy dx or in polar coordinates, I'm just going to say, well, let's remember the definition of the center of mass. It's the average value of a function x in the region. So it's 1 over the area of the region times the double integral of x dA. Right? If you look again at the definition of x bar, it's 1 over area double integral of x dA. Well, maybe, if there's a density, then it's 1 over mass times double integral of x density dA. But if density is 1, then it just becomes this. So, switching the area, moving the area to the other side, I'll get double integral of x dA is the area of the region times the x coordinate of the center of mass. The area of the region is pi because it's a unit disk, and the center of mass is the center of the disk, so its x bar is 2. And I get 2 pi. Okay. Now, I didn't actually have to do this in my example today, but I thought, that would be good review. It would remind you of center of mass and all that. Okay. Any other questions? No. Okay, so let's see. Now that we've seen how to use it in practice, how to avoid calculating a line integral if we don't want to, let's try to convince ourselves that this theorem makes sense.